All right, my friends. Come on, iPad, turn on. It doesn't want to. It never wants to. It's like, no, we cannot do work today. All right, let's look at this question, and we'll do two of these together, and then we will do a couple on our own. Average isotopic mass. Do you remember what an isotope is?
No. It's like the same element, like different mass.
I can't hear anybody because there's a lot of... This is the white noise I hear in the background. All right, Panak, go ahead. Same element. So if they're the same element, they're going to have the same number of protons. And they're going to have different numbers of neutrons. Okay. They might use the word atomic number here, just so you know. They might use the word mass number here, just so you know. They could have the same number of protons or the same atomic number, different number of neutrons or different mass numbers. And they look, when we write them in isotopic notation, something like this, where the top numbers are different and the bottom numbers are the same. All right. Now, we left off talking about average isotopic mass yesterday. When you're doing average isotopic mass, it is dependent upon the mass of the atom and the percent abundance of that particular atom. Do you remember how we put these together? Ladena, you remember? That was a... No? Okay. Let's look at what we wrote down yesterday. Okay. I said if you have 95% magnesium 24 and 5% magnesium 25, how am I going to calculate the average? Does that ring a bell now? You see what I did? What did I do with the 95%? I multiplied it by the mass after I moved the decimal, right? So I wanted to make sure that this was a decimal, in decimal form. So if we go back to this paper, if I have 22%, I'm going to take 22%. Let's keep it consistent. 22.00%. I don't like this worksheet because of these numbers are like crazy. And we're going to multiply it by 159.3. And then we're going to add to that 78% times 161.2. Now when we actually have to do the math, we've got to change these percents to a decimal. Okay. How do we, I don't know. Because I have to entertain myself somehow. So if we do 22%, we're going to move the decimal 2 places to the left. We're going to end up with 0.2200 times 159.3 and 0.7800 times 161.2. Now before you go and take out your calculators, let's think about what the number should come out to be. It needs to be somewhere between these two masses. It cannot be lower than the 159.3, and it cannot be above the 161.3 or 2. It has to be between those. What is it going to be closer to? The 159 or the 161? 161. So now let's do the math, and let's see if we get a number that's closer to 161 than it is to 159. Oh boy, what did I do? What number did you get? 160. Point what? 782. That's what I got. Okay, that's the average. And notice how it's closer to 161 than it is to 159. Because it's 0.782, which is closer to the 161. Let's try one more. Let's try this one. 42.10 atomic mass units. So this is the mass at 93.5%. I'm going to highlight these two because they go together. This one is 48.30 atomic mass units at 6.2%. And this one is 50.4 atomic mass units times 0.3%. These are the masses, the ones that say atomic mass unit. All right, let's set it up. 93.50%. I'm going to take the percent sign off and I'm going to move my decimal. It's going to be 0.9350 times 42.10. That's the yellow part. Plus 0.06200 times 48.30. Plus, what's the decimal here? It's 0.3%, so what would it be in a decimal form? Hold on a second. Alana, do you know? Move your decimal 2 spaces to the left. 0.003000. Wow, that's a lot of zeros. Okay, times 50.40. All right. Do some fancy mathematics here. Round it to 2 decimal places. Round it to 2 decimal places. Say it loud. 42 point what? 51. Okay. Anybody want to second that? You agree? You got the same number? Did you get the same number? Matt, did you get the same number? No? There's a whole door full of calculators over here. Okay, you're going to have to get yourself one. We good with this number? You agree? Good, because I agree too. That's the number I got. I will tell you, I get them wrong sometimes if I put them in my calculator wrong or something, so be aware of that. All right, I want to look at one more on here, and it's number 12. There is a typo, so let's fix that. This is 65. This is copper 65. Okay, so now let's read it. There are 2 isotopes of copper that occur naturally. They are copper 63 and copper 65. The copper 63 atoms, which occur at 77.93% of the time, have a mass of 62.929601 atomic mass units. And the copper 65 have a mass of 64.927794. Those are some ugly numbers, okay, but they are what they are. How would you tackle this question if you want to find the average isotopic mass? Go ahead.
The first thing we do is subtract 77.93 to get the other percentage.
That's what I would do. Okay, hold on. Let me just explain that on the videotape here. Okay, because they told us it was 77.93% copper 63, and we know that the whole sample needs to be 100%, we would have to take 100 minus 77.93 to get 22.07, is that right?
Yes.
22.07% of the copper 65. That was not given to us in the words up here, but we need that information in order to calculate the average mass. So now what would we do next? Izzy, what would you like to do next?
Set up the equation.
Yep, so what number do you want to put down first? Okay, let's move the decimal. 77.93 becomes 0.7793. And what are we multiplying that by? 60. 62. They tell us that it has a mass of 62.929601. Okay, use the mass, not the mass number. Use the actual mass. If they give you a mass, you use that mass. Don't use the mass number. Okay, and then we have to add to it 0.2207 times 64.927794, because that's the mass of copper 65. And then we do some fancy math. 77% of the time we had a 63, and 22% of the time we had 65. So my answer better be closer to 63 than it is to 65. See if you can get a number. Abraham, you have a number? No? Maybe? Michelle, you have a number? Nice and loud. 2? Just round to 2 decimal places. How do you feel about that number? Does it look like a good number?
Yes.
Okay, that's the number I got. So we're gonna call it a day, right? We're gonna call that a good number, good answer. Okay, that's how you do average isotopic mass. The last thing I want to do with you today, real quick. Let's go here. Oh, somebody wants us. He's back. I want to go to June of 19, and I want to look at a question because I stumbled upon it this morning, and because I was looking at isotope questions, and I wanted to know if you guys could think about that question and give me an answer, okay? This is what it says. The atomic mass and natural abundance of the naturally occurring isotopes of hydrogen are shown in the table below. The isotope H2 is also called deuterium, as usually represented by the symbol D for heavy water, forms when deuterium reacts with oxygen to produce by producing molecules of D2O. Okay. Explain, in terms of subatomic particles, why H1, H2, and H3 are electrically neutral. Okay? We can't do 53 and we can't do 54, but we can answer 52. Explain in terms of subatomic particles. So let's dissect this question. If it says in terms of, that means you better be talking about those terms. What is a subatomic particle? So in your answer, you need to use protons, neutrons, and or electrons. Okay? Go ahead. You wanted to add to that? And if there is the same number of protons, that's using the word subatomic particle in there, right? And the same number of electrons, is the atom going to be electrically neutral? Yes. So there's the answer. That is the correct answer. Now, you cannot say, this is what you cannot say, it is electrically neutral because it has no charge. Although that is a correct statement, it is not telling me the answer in terms of the subatomic particles. So you needed to say it has the same number of protons as electrons. Now the whole question up on top where it says naturally occurring isotopes of hydrogen, in an isotope, what changes? The number of neutrons. Did this question number 52 have anything to do with neutrons? No. They're trying to play a trickaroo on you. Okay? Don't let them do that. You know the answers, you just have to kind of put them out there. Okay? So this whole test is going to be a reading test, making sure you read the question carefully and figure out what they are actually looking for. Okay? Now, I assumed when I was looking through these Regents questions that because they had this table, they were going to ask for the average isotopic mass of hydrogen. Did they give you enough information to calculate the average isotopic mass of hydrogen? Yes, they did. They gave you the abundance, which is the percentage, and see the little percent sign right here? And they gave you the mass. But they didn't ask that question. They asked a totally different question. So be careful with that stuff. Now, every Regents exam, let's go to June of last year. Every Regents exam is going to have a question on average isotopic mass. It's just a matter of finding it. Sometimes it is going to be on part A, which is multiple choice. Sometimes it is going to be on part B or C, which is going to be short answer. This happens to be short answer. So let's take a look at this question real quick. It says silicon is an element in group 14. You don't know what group 14 is yet, so let's just move past that. The periodic table, you know what that is. The atomic mass and natural abundance for 3 naturally occurring isotopes of silicon are shown in the table below. So here's the percents. Here's the masses. Okay. You don't know how to draw a Lewis electron dot diagram yet? That's coming up in the next week or so. Compare the energy of an electron in the first shell to the energy of an electron in the third shell. You know the answer to this one already. At least I hope you do. What happens to the energy as you move from the first shell, which is the ring, to the third? Kevin?
Like there's more electrons, so I guess it goes down.
No.
Energy increases as you get further away from the nucleus.
Energy increases as you get further from the nucleus. So it says compare the energy of the electron in the first shell, that's the first ring, to the energy in the third ring. Who has more energy? Say it again. The third shell. I hope you said third shell. It's hard for me to hear you. Okay, the third shell has more energy than the first. That's the answer to that question. Okay? You know that already. We didn't draw them yet, but you know it. All right, now, number 55 is what we were working on this period. Show a numerical setup for calculating the atomic mass of the element silicon. What would that look like? I think I closed down my thing already. Okay, let me just squeeze this. Oh, I didn't. Here it is. Okay, so can I move this over just a little bit? Okay. Show a numerical setup. Let's take the percent, 0.9222. That's that number right there. 0.92, see 92.22? I moved the decimal over. Times the mass, which is 27.98. Plus 4.69. How do I change that to a decimal? 0.0469. What am I multiplying it by? 28.98. And finally, 3.09, which is going to be 0.0309 times 29.97. And I'm done. Does it say give me the answer? No, it says show the numerical setup. This is the numerical setup that they're asking for. It's on every Regents. Don't throw away those 2 points. Last year, when we got our statistics back, 47% of the students at Comstock High School got this question right. That means 53 got it wrong. And I don't know why, because it's really not a hard question, and I'm telling you it is on every region. Take those points and stick them in your pocket. They're yours. Okay? And they always look like this, or they might write it in words like I just showed you on the other examples. Okay? Any questions? I'm going to stop the tape. Okay.